welcome to the deep dive. Today we're tackling something pretty fundamental but often tricky, IT blueprints. We're talking about the hidden architecture, the logic behind, well, everything digital, social media, software on your computer. Our mission today is basically translation. We want to take the visual languages of system design, specifically system diagrams and flowcharts, and give you the quick guide to reading them instantly.
Exactly. It's like learning the grammar behind how things get built in IT. You might be looking at a doc for a huge cloud setup, or maybe something simpler like an automated email process. You need to understand not just what it does, but how it's structured, how it, let's say, thinks.
Right.
And the sources we're looking at today, they really lay out the core ways people draw these things, the standard notations. Our goal is to boil down what makes each visual different, its purpose, its key parts. So you get a fast-tracked understanding how these IT ideas get mapped out, long before anyone actually writes code.
Yeah, think about it like this. If we wanted to design, say, a new sign-up process for a streaming service, we'd need two big things, right? First, a map showing the servers, the databases, how authentication works, all the pieces. And second, the step-by-step guide for what the user actually does. Click here, enter this, confirm that.
The structure and the process.
Exactly. And that's basically the difference between system diagrams and flowcharts we're diving into. We're decoding the symbols so you can grasp the whole design idea behind them. Okay, let's unpack this. So let's start with that first part, the architecture map. System diagrams. If you see a bunch of boxes connected with lines, odds are you're looking at some kind of system diagram. It's the structural overview. But the sources point out pretty quickly that structural map can mean different things. Not all these diagrams are the same.
That's right. A system diagram, at its core, shows components and how they're connected. But what components and what kind of connections you choose to highlight? Well, that determines the specific type of diagram you're actually dealing with.
Okay, so the most common one, especially for a foundational view, is the block diagram. These seem great for showing the main parts without getting lost in the weeds. What's the key feature here?
The key is that block diagrams focus on logical groupings or subsystems. So back to your streaming service example. A block diagram wouldn't show, say, server rack 4B. Instead, you'd see a big box labeled something like user authentication service. Another one maybe payment processing API, and perhaps video content delivery network.
Functional chunks.
Exactly. They show the functional relationships, how the big pieces depend on each other, not necessarily the specific hardware or wires. Think of it as the high-level org chart for how the system works.
Got it. So block diagram tells us what the major pieces do. But what if you're, say, a network engineer, and you need to know how those pieces are actually wired together, physically or, virtually? That's where we need a different view, right? Like a network diagram.
Precisely. If the block diagram gives you the logical function, the network diagram shows the connectivity, the actual infrastructure. This is where you'll see icons for firewalls, routers, switches, maybe specific servers. It shows the network topology.
Topology.
Yeah.
Like how it's all laid out.
Yeah, or the connections set up in a star shape.
Yeah.
A mesh,
Yeah.
a ring,
Yeah.
And understanding that topology is critical because it directly impacts things like reliability, speed, how data actually travels between devices.
Yeah.
It's the difference between planning the city blocks, that's the block diagram, and tracing the actual fiber optic cables running under the streets. That's the network diagram.
That clicks. Block diagram.concept. Network diagram.infrastructure. But the third type mentioned in our sources, the data flow diagram, or DFD, that feels different again. It's not static components or wires. It's about movement.
Exactly. It's the dynamic map. The DFD shows the journey of data through the system. It focuses on inputs, outputs, where data gets processed, and where it gets stored. It tells a story. User clicks sign up. Okay, where does that click data go? Which process handles it? Where does it end up getting stored?
So it traces the information itself?
Yes.
Yes.
And what's fascinating here is BFDs add another layer because good practice involves thinking about logical versus physical flow. A logical DFD just describes what needs to happen, technology aside. Like, user data must be validated. Simple. A physical DFD shows how the current system does it. Data gets validated by a Python script on server 3, which connects to database alpha. See the difference?
Okay. More specific.
Right. So these three block diagrams for components, network diagrams for connectivity and topology, and DFDs for data movement, they really do serve fundamentally different needs. Choosing the right one for the job is, well, step one for clear communication about a system.
Okay, that covers the what and the where of the system. The architecture, the hardware, the data paths. But like you said, a map doesn't tell you how to get from A to B step by step. For that, you need instructions. And that shifts us from system structure to process logic. Which brings us neatly to flowcharts.
Right. A flowchart is quite different. It uses a standard set of shapes connected by arrows to show the sequence of steps in a process. It's basically the recipe card for how something should happen, defining the order of operations.
Mm.
It's important to stress, especially for people working in tech, this isn't just making pretty pictures. The shapes used in proper flowcharts are standardized. Think ISO 4807. That standardization is key. It's why they work so well.
That standardization is everything, isn't it? The power is that the shapes mean something specific. If you just learn, 4 or 5 basic shapes, you can pretty much read the logic of almost any automated process or algorithm. The arrows obviously show the direction, the sequence, but the shapes are the actual commands or questions. Let's quickly walk through the essential ones. We've got the ovals, right? Sometimes called terminators. These are the start and end points. Super clear. Every process mat has to begin somewhere and finish somewhere.
Yep, the bookends. Then, after the starting oval, you'll almost always hit a rectangle. This is the workhorse shape. It just means do something, an action, a task, a processing step. In that sign-up example, a rectangle might say, collect user email or hash password. It's an instruction.
Okay, straightforward. But then things get interesting with the diamond. This one's different. The diamond signals a decision point, right? A question needs to be answered.
Exactly. It's where the process might split.
Yeah.
It always contains a question that can be answered with a simple yes or no, or true-false. Like, does email address already exist in the database? Yes. Go this way. No. Go that way.
That branching is key.
It's absolutely crucial because that diamond shape, it's literally the visual equivalent of an if-then-else statement in programming. If you can clearly state the question inside the diamond, coding that logic in Python or Java or whatever becomes much, much easier. It practically writes itself.
Let's try a non-tech example to really nail it down. Making coffee. Start oval. Then maybe rectangle. Add coffee grounds. Then a diamond. Is water reservoir full? If yes, arrow goes to rectangle, press brew button. If no, the arrow goes to rectangle. Fill water reservoir, and then maybe loops back before press brew button.
Perfect example. That diamond controls the flow based on a condition.
And here's where it gets really interesting. You mentioned standardization. The source material we looked at had this reference, flowchart to code example Python 3. It really highlights how the discipline you use in drawing the flowchart translates directly into writing clean code. If your flowchart logic is tangled or unclear, your code probably will be too.
Absolutely. And we can't forget one more common shape, the parallelogram. While the rectangle is for processing actions, the parallelogram specifically represents input or output, data coming into the process or going out of it.
Like reading data from a user form or displaying a success message.
Exactly. Receiving the filled out sign-up form would be input, parallelogram. Sending that confirmation email would be output, parallelogram.
Okay, so those core shapes. Oval for start 10, rectangle for doing stuff, diamond for decisions, parallelogram for I/O. Their clear sequential nature is what turns a general idea into something predictable, something you can actually build and test.
And importantly, something you can debug visually before writing code, potentially catching logic errors early. That saves a lot of time and headaches.
So we get the language now, the shapes and diagrams, but let's talk value. Why bother? We're talking about smart people, developers, architects. Why spend time drawing these things instead of just, coding or talking it through? Seems like extra work.
It can feel like that initially. I get it. It seems like a detour. But if we connect this to the bigger picture, the time you spend making a clear diagram is usually tiny compared to the cost of confusion, rework, or fixing bugs later on because people didn't share the same understanding.
Right, the cost of miscommunication.
Precisely. And the sources we reviewed really hammer this home. The core benefits are pretty consistent across any kind of algorithm or system design. First, they make complex things easier to grasp visually. That alone boosts communication and collaboration, especially when you have different teams working together, like business analysts, developers, QA testers, and maybe, obviously, clear documentation. Someone leaves the project. The blueprint is still there, understandable.
I think for the folks actually using or maintaining the system later, the big wins are around efficiency and troubleshooting. It's hard to spot waste just by looking at lines of code or raw data sometimes, but when you map a process out in a flowchart, you see the steps. You're forced to visualize the flow.
You can spot the bottlenecks.
Exactly. Finding bottlenecks in a flowchart Maybe that looks like a crazy tangle of diamonds, too much complexity in one spot.
Hmm.
Or maybe it's one specific rectangle, one action step that you realize takes way longer than everything else.
Right.
Drawing it makes that slow point obvious. And once it's obvious, you can target it, improve efficiency, cut down errors. You can't really optimize something you can't clearly visualize.
And that actually brings up a crucial point, sort of a balancing act. While visualization is powerful, you can also go too far. An overly complicated flowchart, maybe with diamonds nested inside diamonds 5 levels deep, it can become almost as hard to read as bad code.
The diagram defeats its own purpose.
Exactly. So effective diagramming isn't just about knowing the shapes. It's a skill of abstraction. Knowing when to group several small steps into one logical block, or maybe define a separate sub-process flowchart to keep the main one clean. It's about managing complexity. So the diagram remains a useful communication tool, not another problem to solve.
That's a really good point. The goal isn't just draw it all, it's communicate clearly. Being able to chunk a complex system into logical blocks or a process into those standard shapes. It's more than just technical neatness.
It's vital for quality control, for getting everyone on the same page for big projects. When everyone agrees on what that parallelogram means, we need input from System X here. Sufficiently, dependencies and timelines become much clearer.
Okay, let's pull this all together. Quick recap of our deep dive. We looked at system diagrams first. They map the structure, components, connections. Could be high-level functional pieces in a block diagram, actual devices and layout in a network diagram, or the path data takes in a data flow diagram, different maps for different needs.
And then we switch gears to flowcharts. These map the process, the sequential logic, using those specific standardized shapes. Ovals for start and end, rectangles for actions, parallelograms for input-output, and that critical diamond for decisions, for the yes-no branching.
The bottom line seems to be that these aren't just sketches, they're formal, efficient tools. They help you build things correctly and maintain them later.
Right. They take complex ideas floating around in people's heads or buried in code and turn them into a shared, precise blueprint that cuts down ambiguity, prevents mistakes, and ultimately saves time and money.
So what does this all mean? It means you now have, basically, the foundational vocabulary. You can look at these diagrams and understand the blueprints of modern IT. You see beyond just boxes and arrows, you see the intended structure, the flow of information, the decision logic. And thinking about flowcharts specifically, they're designed to visualize logic, find inefficiencies, right? Find those sticking points. So if the goal is to untangle complexity, maybe try applying that core logic start, action, decision to one tangled process in your own work this week. Not necessarily IT. Think about it. Which decision point, which diamond in your workflow causes the most delays or confusion for you right now? Mapping that out, even roughly, might be the first step to actually fixing it. Visualize the bottleneck to eliminate it.